Hi everybody, this is the video for lesson 5, mechanisms of reaction from our kinetics unit. So this idea is that because collision theory requires for particles to collide with the correct orientation, this reduces or this correct orientation requirement means that reactions that have more than two particles are going to be very unfavorable. So, for example, in this NO2 example that we did in class, if you were to have this chemical reaction with two nitrogen monoxides and an oxygen reacting with each other, we could have both of them happen at the same time. Both reactions happen at the same time, sort of squeeze that oxygen and steal it. But this would probably require that both nitrogen monoxides be exactly a perfect, maybe a perfect 180 degrees. So that means there's only one out of 360 degrees that this reaction would even happen. That's a pretty low chance of happening in the chaotic world of the reaction vessel, because they would also have to be doing this reaction with the right amount of energy. So more likely we get some sort of intermediate stage. So this is our intermediate stage where the particles are in some sort of higher energy state, but maybe even a little bit of a stable state. So here we have a 1 nitrogen dioxide, 1 nitrogen monoxide, and a free oxygen. And so this state, although more unstable than the original state, it might be doing some calculations, doing some experiments, computational experiments. You could probably determine that this actually is a state that exists in nature, and increases the chance of this chemical reaction happening. Instead of depending on there being 3 exact particles ready to react at the same time, now we only needed 2 particles at a time to react. These 2 particles react first, then these 2 particles react second. And so in both cases, the reaction only depends on 2 particles. And 2 particles are going to have a higher chance of reacting than depending on 3 particles to react all at once. Okay, so then we extend this to talking about something called a reaction intermediate. These are chemicals that are created during a chemical reaction, but neither a reactant nor a product. They're sort of temporary arrangements of atoms that are created and destroyed during the chemical reaction. These are somewhat stable arrangements of atoms, unlike transition states, which are defined by their instability. So something I didn't mention in class is in this nitrogen monoxide diagram, what we would actually be looking at is, we're probably looking at, in our potential energy diagram, is to take what we had before, which was 2NO and an oxygen. There's initially some energy to cause that NO to collapse, but then there will be a little intermediate stage where we have 1 NO plus 1 NO2 plus 1 O. And then there'll be a little bit more energy, and then they can stabilize into their final arrangement, which is the NO2s, 2 NO2s. So this is more or less what the reaction the reaction diagram probably looks like when we do this experiment. Because the second bump is lower than the first bump, we can't really detect its effect on the chemical reaction. We've already put in enough energy to cross that first bump. We've already brought our system up so that it can cross this first bump. It doesn't even notice this second energy requirement to finalize this chemical reaction. So that's why from a experimental, we end up only looking at a graph that looks like that. As we can't detect short-lived intermediate. Most of the time. There are definitely a lot of chemical practice and chemical experimentation that goes into studying these intermediate stages, and there are some interest in capturing those stages, but that's for advanced chemistry. So this would look like something like this, where we have step 1, a chemical reaction of the nitrogen monoxide and the oxygen. They produce this single oxygen. The single oxygen gets used up right away, so that makes oxygen an intermediate. It is first appears on the product side, secondly appears on the reactant side. They always cancel out in the final net equation. The net reaction represents only the reaction products in their stoichiometric ratios. Catalysts and intermediates are not represented in the net reaction. Usually. Sometimes a catalyst might be added, but it'll be added both the left and the right, so it technically cancels out in a net reaction. So here is a reaction mechanism of nitrogen dioxide. In nitrogen dioxide, one of the nitrogen dioxides actually acts as a catalyst. So it first appears on the left to cause the formation of an NO3, a nitrogen trioxide intermediate. And then that nitrogen trioxide intermediate reacts with the carbon monoxide, and the nitrogen dioxide is reproduced. So this is essentially a catalyst of nitrogen dioxide. As an experimenter, you might have had some problems with your experiment if you didn't provide an excess of nitrogen dioxide. Because if you used only exactly as much nitrogen dioxide as you thought you needed, then that nitrogen dioxide would get used up, and then there would start to get used up, and then there wouldn't be enough nitrogen dioxide left to catalyze your reaction. So that's one way that we would have found that experimentally. The nitrogen trioxide is produced in the first step, but it is used up in the second step, so that makes it an intermediate. All right, so we can look at this example number 2. Here, ozone does have a reaction where it breaks down into O2 and oxygen, and then that oxygen can add to ozone again to form O2 and O2, so it's a 2-step reaction. But these are considered pretty slow. This is a slow process. Usually, it requires the input of UV rays to cause it to break down, and then there's still an activation barrier to recombine. So, if chlorine is free in the environment, which for many years this was a problem, then when we get to the second stage of O2 plus oxygen, a second reaction might be ongoing at the same time. So if there's free chlorine around, then the free chlorine can react with the oxygen, with the ozone as well, in a side reaction, forming O2 and ClO. And this reaction is quite quick. This is very fast. Very fast. And even though this is slow. And then that reaction also reacts with that byproduct, that intermediate, the ClO, reacts with oxygen in another fast reaction, and we get the formation of O2. And so overall, we still get the 3 O2s we got before, but now, and the same 2 O3s, but we can see that the Cl cancels out, that's our catalyst. The ClO cancels out as our intermediate. The oxygens even cancel out as intermediates. leaving us with 2 ozones go in and 3 oxygens come out. So before we had 2 slow reactions that were required, and now we have only 1 slow step and 2 very fast steps. So this reaction is much more dangerous because notice that at the end, the chlorine is regenerated. Regenerated catalyst. And so that's bad news. That means that chlorine is never going to leave the environment. And this is one of the reasons that they banned the use of chlorofluorocarbons in the production of coolants for refrigeration, because chlorofluorocarbons would break down and release free CO, free chlorine into the environment. All right, do I have anything else to say here? The rate determining step of a chemical reaction is the slowest step in the reaction mechanism. Typically, this implies that the step has the highest activation energy. It is the least likely to occur. In both of these reactions, the rate determining step is probably that ozone breaking down into oxygen and a free oxygen. I'm going to rewrite this one to match our new story. This is going to be moderate. Okay. So let's look at this reaction mechanism here. So notice that in this reaction mechanism, we add everything together. We did this in the live stream, and you can see the summed net reaction here. Terrible print. I think it must have been writing over my shoulder or something. So like this. So we get this summed reaction, but we notice that the reaction intermediates, we identified those, X and Y, but notice that in the rate determining step, we only have P and Q. So this is the slowest step of the reaction mechanism. So we are talking about a reaction mechanism that looks something like this. It starts out with P and Q and S. We have the original setup. We're going to have some products. It doesn't matter. Let's do this one as an endothermic. We haven't done an endothermic one yet. This is where you're going to have your 2 T's plus your R. And then there's going to be the slowest step. Whoa. Try to draw that one a little bit more smoothly. The slowest step will have this high energy barrier, and then a stopping point where you now have X and T plus any other reactants you need, P. And then there'll be a little tiny hump, and then another stabilizing barrier or a stable state, Y and S, plus any other products that you made, so plus R and T. And then the last hump, and then back down to form this last thing here. So I'm just going to grab the whole thing, move it down. I'm going to grab my axes, move them up. Something like that. So this is potential energy, and this is reaction coordinate. So if this is an endothermic reaction, that's what it would look like. This first step is the slowest step. So this is the slow step. It is the least favorable. It has the highest energy barrier to get to it. Notice that if you increase the P or increase the Q, then the rate will increase. But if you increase any of the other elements, like S, it has no effect. All right. And then there was some practice questions. You can check out those. I think I did these on the live stream. If not, you can look at the PDF online and see those answers. All right. Best of luck to you, and we'll talk to you soon.